Hi folks, my name is Dan Knighten and I'm the General Manager here at Audio Precision. Today I'd like to show you how we can measure a set of Bluetooth earphones with our friend Kemar and our brand new APx517 Acoustic Audio Analyzer. First things, let's just position our headphones on Kemar. Got a good fit there. Next, let's unbox our brand new 517. Little box of goodies. Need a couple of those in a second. And then here's our brand new 517. Straighten up our Bluetooth antennas, because of course the electrons do know what position they're pointing in. All right, we need our power cable. We'll go ahead and plug that in. And as I plug that in, what I hope you don't notice is the noise that 517 makes. It's the first audio analyzer we've designed at Audio Precision with thermostatically controlled fans, making it inaudible in a typical office environment. I'll plug in our USB cable and I'll start the software. Now we do have to make some connections here, but the nice thing is that everything we need to acoustically measure these headphones will plug directly into 517. So we can drive the mouse simulator on Kemar, which we'll use to measure the Bluetooth microphone, directly from our power amplifier output. We'll get the signal from the earphones directly from the ear simulators that we can plug directly into our mic input 1 and 2. And finally, one additional connection I'll make is when we want to measure the microphone embedded in these headphones, I'm going to do it by reference to a measurement microphone at the mouth reference point in relationship to the mouse simulator. And to plug that in, I'll actually use our balanced input with a convenient adapter. So we do have a few cables going on here, but each one has a home directly on the front panel of 517. Now, the other thing we have in this analyzer, of course, is our Bluetooth interface. And of course, we don't have any cables going to our earphone right now. We're going to do that all wirelessly. So on my output, I'm going to select Bluetooth. My profile mode will be A2DP source HFP audio gateway. Now, I have previously paired to these headphones, so they'll actually connect automatically once I turn them on. And I'll just go down here and connect all the profiles. That actually happened automatically, conveniently enough. And then for the input side, I have two input connectors. They're both unbalanced, and they both need CCP power. And I'll go ahead and put the input into acoustic mode. And I happen to know my friend Kimar well, and his sensitivity is 18 millivolts per Pascal. So I'll just enter those values. And now we'll start out with just getting the frequency response of the earphone drivers. I'll add our acoustic response measurement. And I'll go ahead and sweep from 20 Hertz to 20 kilohertz. Let's do that at minus 10 dBFS. And let's do a 2.5 second sweep. So one thing that Bluetooth headphones often have is quite a significant amount of delay. You'll notice that we're measuring a delay of 15.3 milliseconds. I'll go ahead and extend my acquisition time by let's make it a full second to make sure I capture the entire response. And I'll want to go ahead and set my time window well beyond that point to make sure I'm not windowing out the response by mistake. If I look at the energy time curve, here we can see a bit of the delay in our system. But by setting the time window well outside of that and making sure our acquisition encompasses all of that, we can now look at just the frequency response of these earphones. We of course get the absolute response in dBSPL, the normalized response centered at 1 kilohertz. We can look at the phase response, the THD, the rub and buzz, and all the other normal properties we'd look at in an earphone driver, even though in this case we're connected to it via an RF wireless connection instead of with an analog audio cable. And again, a few more connections involved, but we can get this all set up very quickly by taking advantage of the integration in the 517. Now what I'll next do is let's take a look at the Bluetooth microphone. So I'm going to add a signal path. Now my output is going to be physically the mouse simulator, which is connected to our 517's power amplifier output, so the default there is actually good. For the input, I'm going to use this reference measurement microphone, and that is actually connected on the balance connector. I only have one channel of that, and what I'll do here is I actually need to pass it 48 volt phantom power. And I'm going to calibrate it the old-fashioned way. That is to say, I'll actually put a mic calibrator on it, our Grass 42 AG. So we have that side calibrated. Now the next input is going to be a little bit interesting. Here I'm going to take advantage of the ability to have two inputs active. And for my second input, I'm going to select Bluetooth. So here I'm going to just test the same headphone, but I'm going to connect the HFP profile. And by looking in the status bar, I can verify that we're connected via Bluetooth to the device. and I'm going to open a SCO channel. And now you'll notice that in my input signal monitor, I actually have two FFTs. One is the signal from the analog reference microphone, and one is the signal from the Bluetooth microphone received wirelessly. And I'll go to Verify Connections, and I'll just generate a signal from our mouse simulator. And I should see that in both inputs. Both the reference microphone is picking it up, and then the digital Bluetooth microphone is also picking it up. So now to measure this microphone, there's a few different techniques we're going to use, or could use. I'm going to use transfer function. And in transfer function, I'm going to play back a speech file. So not a sine wave, but actually simulated human speech. And what I'm going to do is that's going to come out of the mouse simulator. And what I want to do is now perform a transfer function between input channel, and I'll use as a reference our reference microphone at the mouth reference point, and I'll compare the Bluetooth microphone to that. And I'll just configure my transfer function, and since I'm doing human speech, I'll want to do a bunch of power averages, and I'll do a transform of magnitude only. My signal is 10 seconds long, so I'll just set this up so my acquisition is equal to that. Okay, so we'll go ahead and start our measurement.
The jacket hung on the back of the wide chair.
A pound of sugar costs more than eggs.
The coffee stand is too high for the couch.
The ship was torn apart on the sharp reef.
Okay, and so now what we have on screen is the frequency response of the microphone embedded in our Bluetooth headset relative to the mouth reference point in KEMAR, a standard acoustic reference point. And the further nice thing about this transform is it is giving us this result in the form of sensitivity, or dBFS. So what's coming out of the Bluetooth microphone is a digital signal relative to pascals of sound pressure. So even though this configuration is somewhat more complicated than testing just a passive speaker or an analog headphone, we have all the same integrated capabilities to make a complete measurement of a Bluetooth headphone, all in one chassis combined with the appropriate acoustic fixture.
Find out more at Vicom's website.